Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will discuss the thermal comfort of human being and requirement of comfort air conditioning we will start with. Then we will talk about thermal sensation, oxygen consumption, clothing, effect of clothing on thermal comfort, and environmental indices of thermal comfort. Now, thermal comfort is required, as I've told you in the previous lectures also, to increase the efficiency of working efficiency of an individual. If the efficiency of an individual is maintained, then definitely the production in the industries will increase. That is one thing. Even in the offices, the efficiency will increase if the offices are air conditioned. Because second thing is outside environment never keeps you in a state of thermal comfort. Either you have winter season or summer season, or sometimes temperature is low, humidity is very high in rainy season. So that is why if somebody wants to remain in thermal comfort, an artificially controlled environment has to be created. Now, in this environment, ideally the temperature has to be 25 degrees centigrade and relative humidity of the order of 50%. But outside in the world it does not happen. So you have some thermal sensations. I mean, you may feel hot, you may feel warm in the outside environment, you may feel hot, you may feel cold, and you may feel chill. But say as an engineer we have to, quantify these things, right? In order to quantify, ASHRAE has quantified the thermal sensation, and it has given certain points. +3 is hot. We start with the 0. 0 is neutral. Then +1 is slightly warm. +2 is warm. Similarly, -1 is slightly cool. Then -2 is definitely cold, and -3 is severely cold or chill. So these are the chill. So these are the indices by thermal indices. And now ASHRAE has given equations for male, for female, a generalized equation, and there are number of equations. But Stroker, if you refer this book of Stroker, you will find that he has given one generalized equation: y is equal to AT plus BP minus C. Now for A and B, a table is given. This is number of hours, exposure for number of hours, and for A, B, C, a table is given. Suppose exposure is for 1 hour, the value of this value is 245, 0.248 minus 6.475. If exposure is for 2 hours for a particular environment, then it is 0.252, 0.240 minus 6.859. If exposure is for 3 hours, then 0.243, 0.278 and minus 6.802. So Stroker has simplified this. Now suppose somebody is exposed to an atmosphere. Now we can take the conditions. suppose an individual is exposed to the atmosphere at let us say 30 degrees centigrade. Now, if somebody is exposed to 30 degrees centigrade, the feeling of warmness or coldness will also depend upon the relative humidity. I mean, temperature is not the only governing factor. So, since it is going to be related with the relative humidity, saturation pressure of water vapor at that particular temperature is also taken account here. So, P is the saturation pressure of water vapor at this saturation temperature, right. So, now here we will take the value of saturation temperature from this table. So, if the the temperature at 30 degrees centigrade, so T is equal to 30 degrees centigrade, and partial pressure of water vapor at 30 degrees centigrade is 4.247, right. So, partial pressure of water we have also taken into account, and with this, if I take 1 hour working, so 1 hour working means y is equal to 0.245 multiplied by 30 plus 0.248 multiplied by 4.247 minus, so it is minus C, so it is already, I mean it will be minus 6.475. So y is going to be 0.24 clear 0.245 multiplied by 30 plus 0.248 multiplied by 4.247 minus 6.475, 1.92, y is equal to 1.92. So, this is minus, so here we will take this, right. So, it is y is equal to 1.92. So, 1.92 you will feel slightly warm at 30 degrees centigrade. We can cross verify this. Now, let us go for 3 hours. This is we have done for 1 hour. Now, if we do for 3 hours, then it is going to be 0.243 multiplied by 30 plus 0.278 multiplied by 4.247 minus 6.802, right. So, here if the person is exposed to this temperature for 3 hours, then we get 0.243 multiplied by 30 plus 0.278 multiplied by 4.247 minus 6.802, 1.67. Now, we can make a very interesting conclusion here. Y is equal to 1.92 and y is equal to 1.67. So, 1.92 is more towards warmer, it is warm in fact, and 1.6, so here the sensation of heat is less in this case, here in this case it is more, And it is obvious, if somebody is exposed to this atmosphere for 30 minutes, definitely the body will try to acclimatize. This is the tendency of the body. So body internal mechanism of the cooling of the body will get accelerated, and the feeling of the high temperature will be reduced if he or she is exposed to 30 minutes. And similarly, we can do calculations for lower temperature. You can do it yourself by yourself. Temperatures at, let us say, 20 degrees centigrade or 18 degrees centigrade outside temperature. Let us see if outside temperature is 10 degrees centigrade. Now, outside temperature is 10 degrees centigrade. If outside temperature is 10 degrees centigrade, then partial pressure of vapor is 1.228. Right? And with the help of these values, 0.245 into 10 plus 0.248 into 4.247 minus 6.475. We are getting 2.9. So outside temperature is 10 degrees centigrade. We will get almost chilling effect, right? And chilled, if you look at the chilled water is approximately in a range of 4 to 7 degrees, 7 to 8 degrees centigrade. So at 10 degrees centigrade at outside temperature, you will get almost chilling effect. Now let us talk about this 30 degrees centigrade. We can cross verify this also. Our skin temperature is approximately 33 degrees centigrade. Body temperature is 37 degrees centigrade, but our skin temperature is approximately plus minus 1 degree centigrade depending upon the outside temperature. If outside temperature is high, then skin temperature will also increase to reduce the heat flow to the skin. Outside temperature is low, the skin temperature will go down, and suppose evaporation from the skin, that increases the lowers down the temperature of the skin. Anyway, so it is considered 33 degrees centigrade plus minus 1 degree centigrade. So it can be 32 degrees centigrade or 34 degrees centigrade. Now, if outside temperature is, let us say, we have to find outside temperature. Body temperature, skin temperature is 33. Suppose we are sitting in outside environment, doing or not doing any activity, the heat liberated from the body will be 100 watts. There is a breeze. In that case, H can be taken as 10 watt per meter square Kelvin. Area we have calculated in the previous lecture. Maybe you can take 1.7 or 1 point, let us take 1.8 meter square Kelvin. So only meter square, not meter square Kelvin. With this help, suppose all the heat is dissipated by convection heat transfer. So 100 is equal to, Q is equal to H A delta T. So H is 10. For the sake of convenience, I have taken these simplified values. 1.8 into delta T is going to be 100, right? And if this 100 is divided, this is 10 divided by 1.8, and that is going to be approximately 10 divided by 8. 10 divided by 1.8. 5.5 approximately. These are all approximate values. So delta T is 5.5. It means if body temperature is 33 degrees centigrade, outside temperature has to be 5.5 degrees centigrade less than this. It has to be 28.5 degrees centigrade. 27.5. 27.5 degrees centigrade. If outside temperature is 27.5 degrees centigrade, all 100 watts of heat will be liberated. But as we know that part of this heat is also taken away by the evaporation from the skin. So that is why you must have realized that when outside temperature is 29 degrees centigrade in the month of February or March or in the month of September, you start feeling slightly uncomfortable because convective heat transfer is not sufficient. So, either you increase the H by blowing air over the body, or that is one way of enhancing the heat transfer. That is why when you are sitting in the fan, when you are sitting under the fan, this H increases. This H increase will reduce the delta T. It means instead of feeling comfortable at 27.5, you may start feeling comfortable at 29 degrees centigrade, or for that matter 30 degrees centigrade. That is why when the weather is extremely hot and you are coming from outside and sitting before the fan, you feel extremely in an extreme state of comfort. You feel very comfortable. The reason being the value of H increases in that case. Now, value of H for the air when it is less than 0.2 meter per second, in that case the value of H is 325 watt per meter square Kelvin when the velocity of air is less than 0.2 meter per second. But otherwise, if the velocity is more, in that case there is a correlation 8.3 V raised to power 0.6. Now, using this correlation you can find the value of, suppose velocity is 1 meter per second. If velocity is 1 meter per second, in that case you can find the value of H as 8.3 watts per meter Kelvin, right? If you are walking, if you are walking, you are not sitting, suppose you yourself is walking, in that case this relation is slightly modified, it becomes 8.6, or this curve tends to be flatter 0.5.3. So, if the air is blown over you with 1 meter per second, H is 8.3. If you are walking 1 meter per second, in that case, I mean 1 meter per second is not very fast walking, 1 meter per second is 3600 meter per hour, it is 3.6 kilometer per hour. This is normal walking speed, that is not very high walking speed. So, if you are walking 1 meter per second, the value of H is going to be 8.6. So, instead of air is blown over you, if you walk with this same speed, the value of H is higher, right? Now, in air conditioning environment, suppose I am sitting in air conditioning environment wearing only a half sleeve shirt, another person is sitting with a suit. So, the person who is wearing a suit definitely demand lower temperature. He will say that I am feeling comfortable at 22 degrees centigrade. I am wearing half sleeve shirt, I will say I am feeling comfortable at 25 or 26 degrees centigrade. So, this clothing also, because these clothes act as an insulation, and clothing thermal efficiency is TCL minus TO divided by TSK minus TO. It means temperature of cloth, suppose temperature of this cloth, outside temperature divided by skin temperature minus outside temperature. That is clothing efficiency, right? If the cloth temperature is outside temperature, then efficiency is 0. Now, so the cloth also offers a resistance R, thermal resistance, and this thermal resistance is equivalent to skin temperature minus outside temperature divided by heat flux minus 1 by HFCl. It is nothing but simple equation of conduction and convection heat transfer. Through that equation it has been driven. This is the resistance offered by skin and outside. This is film coefficient, film resistance, because when convective heat transfer over the cloth, a film will be formed over the cloth. So that resistance has the difference of these two resistance will give the clothing resistance, right? Now this clothing resistance is expressed in terms of CLO, and 1 CLO is equal to 0.155 meter square Kelvin per watt. Now I will show you one diagram related with the comfort with clothing. Now these are ASHRAE summer and winter comfort zone, but since inside environment is same, so it has to be same. ASHRAE assumes inside temperature 24 degrees centigrade. But if you look at the summer and comfort zone, this is 0.5 CLO. This is equivalent to summer clothing, like my clothing. My clothing will be approximately 0.5 CLO. Now, if you go to the winter clothing, I am wearing a suit or a coat, or in that case, it is going to be approximately 1.0 CLO. And the data are based on the ASHRAE standard 55. Air speed is less than 0.2 meter per second. You can see, but they are not very distinctive boundaries. Operative temperature, acceptable level of operative temperature, it is, say for winters, if you are heavily clothed, it is starting from 21 or 21.6 or 21.7, and when the humidity ratio is increasing, the operating temperature is also decreasing. And when it comes to this, because this is the upper limit of a specific humidity, that is 12 milligrams per kg of dry air, it turns out to be around this is 18.5 degrees centigrade, approximately 18.5, 18 and 21, 3. So approximately 19 degrees, 19.5 degrees centigrade. Then when the specific humidity or humidity ratio is, specific humidity and humidity ratio are same. When it is reducing, this temperature is also rising, and when the humidity is very low, then it is approximately 21.5 or 21.6. Now from here we can infer that for higher humidity we can go for the lower pressure. So if the outside temperature is low, if humidity is high, the feeling of cold sensation will be less. Now when this is summer clothing, and now here you can see again, if the relative humidity is low, we can go up to 28.5 degrees centigrade, and the moment the humidity starts increasing, the temperature keeps on reducing, and this is upper limit. It comes to 27 degrees centigrade. Beyond that, this is not a comfort zone, this is the comfort zone. This shaded area is the comfort zone for summer and winter as well. But under any circumstances, or the specific humidity is not allowed to be more than 12 milligrams per kg of dry air. So this is restricted area, this is restricted area. Here you are not supposed to design the system, and the comfort is confined to only this area, and this is the operative temperature of the surroundings. So this is for sedentary activity. I mean sedentary activities where somebody is sitting, writing or typing when the metabolic rate is less than 1.1 meter. If metabolic rate is high, definitely these ranges will also change. And you can find there is overlapping also. Here I have already told you that these lines are not very rigid lines. They also depends upon the person, which geographic region he or she is living in, or which race they are belonging to. It depends on many factors. But they are statistical data, and they are widely agreed data for internal comfort, or for the comfort of occupied space. Now similarly, we have another graph for air velocities and operative temperature. Now in this graph, on y-axis, air velocity is taken, and on the x-axis, the operative temperature is taken. Now activities, suppose 1 met activity is there, the operative temperature where air velocity is 0, air velocity is not 0, we take approximately 0.2. So operative temperature is approximately 26 degree or 27 degree centigrade, 26 point something. But the moment velocity increases, we can go for higher operative temperature. This phenomena I have already explained you. If air is blowing with a higher velocity, operative temperature will increase. So in this direction, metabolic activities are increasing. Suppose this is 3 meter. 3 met, you can find if the air velocity is 0.2 meters per second. This is for clothing level of 0.5. It is for summer clothing. So the temperature is going to be 13 or 14 degrees centigrade. And this is relative temperature at 50% relative humidity necessary for comfort. Predictive PMV is predicted mean vote. This 0, 1, 2, 3 classification I told you from chill to the hot climate. So predictive mean vote means a person, vote means 0 means a person in this environment or a particular environment is feeling extremely comfortable. Okay. After this, we will start with the last topic to be covered here, environmental indices. Now environmental indices now environmental indices is a combination of 2 or more parameters into single parameter. So just you look at this index, a particular index, and you come to know about the environment. First is effective temperature. Now another one is humid operative temperature. And third one is heat stress index. Effective temperature I have already explained you previously. Humid operative temperature is the temperature of air which is 100% humidified, or relative humidity is 100%, and same amount of heat is dissipated to the surroundings. So that is known as humid operative temperature. Now third one is heat stress index. That evaporation from the skin, heat stress index is observed sweating from the skin, maximum possible sweating from the skin, and this ratio is known as heat stress index. If we have the value of these indices, we can have fairly good idea about the state of thermal comfort in a confined environment. This is all for today. In the next class, we will take up indoor environment health. Thank you very much.